Hello, my name is Jay Smith, and I go to the University of Health Sciences and Pharmacy, and this is my DAM3 final project using PyTorch neural networks to classify CFAR10 images. Here's my background cell, basically computer vision and multi-class classification is very important for a lot of reasons. Here's my hypothesis cells. Basically, I have two different hypotheses. One is for my first neural network, and then the other is for each improvement. Basically, null is that it will be equal to randomly guessing. Alternative is that it will be better. And then for each additional iteration of my improvements to my neural network, null is that it's the same as the previous version. Alternative is that it's gotten better. Okay, research methods. I will be using lots of packages that I describe here, and the CFAR10 dataset. I will look into that more soon, and I will be able to identify the formatting of the training data, testing data, and create my model. The parts of the model are described here. I have model shape, which is saved inside of a class, the hyperparameters, which are set by the coder, and then of course you have the weights and biases within the model, which you can't really see. The coder can't set because there's way too many of them. And then I functionize the training and testing loops, and I evaluate the model using accuracy and train time to compare different iterations of my model and improvements. And then I have a timer and other stuff so that I don't run into problems. And then I compare improvements, recommend the best one. Here are my imported packages. For getting data, I use CFAR10, TorchVision. What is it called? Datasets is how I get CFAR10. And I have transforms, including a grayscale and a 2-tensor transformation, which I use on both the training and test data portion of the dataset. It basically allows my data to go from colored images to black and white images and in tensor format so that I can use it in my model. Understand the dataset. There are 50,000 train data and 10,000 test data. There are 10 different class names, and they are all sorted into 10 different class values, 0 to 9. Since I converted it to grayscale, the shape of the image of a single image is 1, 32, 32. So each image is 32 pixels by 32 pixels. As you can see, every single pixel is a decimal value between 0 and 1. What are these decimal values stand for? Well, if we multiply each decimal value, or the entire image or tensor, by 255, surprise, surprise, they're all whole values, which means that they're all color codes of some sort. Of course, it's not in color, it's in black and white, but that is how it is given after grayscale. I describe that here. Then output shape, and we have label 6 associated with frog. Now we're going to visualize this image. It's 32 pixels by 32 pixels, with the first color channel being grayscale. We have to squeeze the first color channel for the grayscale, and using the image show, what is that called, matplotlib function, we can visualize the frog. Of course, these axes are meaningless. It's the number of pixels actually. So you can see there's 32. And this is our little frog. There are 60,000 images like this in our data set, and that's what we're training my machine learning model on them. Here's a bunch of the images that I do here. It's going to be 30 of them right here. and they're all labeled. So you can see this is airplane, truck, dog, cat, and let's go to this link to show you about the data set. So normally they're in color. You have the 10 different categories and a bunch of them. The one thing that is important to note is that there's no overlap between automobile and trucks, and there's no pickup trucks in the entire data set. So you may think, oh, automobile and truck, what's the difference? But they've got that handled for you. And then for modeling, we're going to start modeling, where you got to set up the hyperparameters. Now, these are just some baseline hyperparameters. Of course, I'm going to change epochs later. I'll change the learning rate and hidden units as well. But batch size, input shape, and output shape are all set. Those are constant throughout the entire program for all my models. And then I'm going to set some device agnostic code and prepare the data loader. The data loader helps us take the test data and load it into our model using torch.dataLoader. I believe that is. Okay. And then visualizing the data loader, basically we give it the batch size and it turns it into batches for us. And if we want them shuffled, they'll shuffle. And we shuffle the training data for randomness and to prevent overfitting, and we do not shuffle the testing data so we have consistency. As you can see, there's 32 images per batch, and we're going to view one batch. This is 32 images, it's in one batch. Our train data loader has a total of this many batches, and our test data loader has this many batches. Let's define some functions. We've got accuracy function. It'll return the accuracy as a whole number, or I mean, it's a float, but it's out of 1 to 100 for the accuracy. And then here's an example of the accuracy function. As you can see, it got this 0 right, this one wrong, this one right, this one right, so you have 75. So you give it two tensors, the true values and the predicted values, and it'll give you the accuracy of the entire prediction. So we'll do this for every batch. And then print train time. This is a function that will involve timing our experiments, so we can see how long they take. Maybe if you wanted to redo it, you would not do some of the experimentations because they take quite a while. Here's an example of that, and as you can see, there's no code in between the two timers, the start time and end time, so you have basically 0 seconds. That's how fast the computer is. And then the initial architecture is going to be our model saved to a class as an object, the init function, and the forward function. The forward function calls to the init self portion with, first of all, we're going to flatten it, take it from 2D to, what's it called? We're going to take it from 2D to 1D. So it's going to be 32 times 32, which is 1,000, it's 1,000 something, 1,024. And that's how many in features we're going to have. Input shape is going to be equal to our, hidden units we're going to change, and right now it's equal to 16 for the baseline. And then output shape is 10. It's going to output 10 different, decimals, like floats between 0 and 1. And it's all going to be the probabilities for each image. And then you're going to take the max probability, and the argmax of that will be the image you want. We'll go through that later. But here's setup for model 1. So we're doing multi-class classification, which means that the best loss function is going to be cross entropy loss. And for the optimizer, you can do a few different things, standard or stochastic gradient descent and atom W, but we're mostly going to be sticking with stochastic gradient descent. That's what I found works best for my type of problem. The loss function you want to minimize. It'll give you a loss value. The lower the loss, the better your model. And the optimizer helps to optimize and minimize the loss function values. Okay. Training and testing steps. I might not read through all of this. I'm just going to show you. But the training step involves the model changing the weights and biases between every neuron in the network. And you don't see this happening, but it happens. And each training step has 5 main steps. And after you go through all the steps for the batches, you calculate the train loss and train accuracy for each epoch. You do the training step and the test step once for every epoch. On the testing step, we are going to turn on the model eval in inference mode, and the testing step is very important because it helps you evaluate the model on images or data images that the model has never seen before, which allows it to allows you to be able to tell if it's actually understanding what it's seeing and able to make predictions without overfitting to the model you give it. And then here's the train step function. We're going to go through, we're going to take these parameters and set our model to training on whatever device we're using. And then for every single batch, we have the 32 images, and we're going to do a batch at a time, these 5 steps. Forward pass is the first one, then we're going to calculate the loss and put that to the accumulator, also calculate accuracy while we're at it. Optimizer 0 grad, this is just resetting the optimizer from the previous iteration, and then we're going to do loss stop backward. This is back propagation and is very important to machine learning. Then the optimizer step helps optimize the loss. And after we go through all the batches in our data loader, like 1500 or something, whatever we saw earlier, we're going to calculate the average loss and average accuracy and return that to save to a dictionary. Then our test step is very similar, except we have the first 2 steps. We are not going to use optimizer 0 grad, loss backwards, or gradient descent. And we're also going to use torch inference mode and model to eval to make sure we're not influencing the model and we're going faster because we don't need the gradient descent memory taken up. And we're also going to return test loss and test accuracy. Next, we're going to create a function for visualizing the loss curve. And not just the loss curve, also the accuracy curve. It's using matplotlib. This is the format of the dictionary, which I'll be using below. And for every epoch, there's going to be 1 new value here. So that's why we take the total epochs here. And it's pretty self-explanatory. We're just going to make 1 graph. We're going to have 2 graphs using those 2 different subplots. And one subplot is going to have loss versus test loss. The other one is going to have accuracy versus test accuracy over time. Time is in epochs. Epochs is going to be the x-axis here. And then you have the 2 different y-axes. Okay, let's keep going. So the first model is going to have 2 epochs. It's using the linear model. Baseline hyperparameters described earlier. We're going to save them to a dictionary, the train and test scores, and we're going to use the timer to see how long it takes. So every single model will have the same structure as this. It'll just have the different model numbers, so I can save them. So that's our dictionary. And after each epoch, we're going to add the 4 different values that we got returned above from these two functions to the model, or to the dictionary, I mean. And then we're going to stop it, and going through 2 epochs takes about 30 seconds. And after that, we have about 25% accuracy. It's hard to see on just 2 epochs how it changes, but you can see the train accuracy increases. Why the test accuracy decreases, you can't really say, but who knows. But you can see for both, the loss decreases as well. So it gives us a baseline accuracy of 25%, which is better than the 10% you would get for randomly guessing. So you can tell that the neural network, even though it hasn't trained very much, it's already working. And it gives us a baseline model to compare all of our other models. So next we're going to use 10 epochs. That's our model 2 adjustments. I have a bunch of models, I think 8, and all of them have different adjustments to make the best version of the model I can. So here you can see I just to change the epochs, everything else in here is the same. And here's the visualization. So we get to interpretation, we get to a maximum of 28 for the test train accuracy, but the testing accuracy is inconsistent. You can see it goes up and down and up and down, and it follows the trend of this, but not as closely as you'd like. Our next adjustment for Model 3, but Model 2 is still better than Model 1. The only thing we changed is epoch count. It's keeping epochs at 10 and increasing the hidden units. What does this do? Visualize it, and it seems to perform better. Or no, the train accuracy remains at 28 actually. But it does do better being more consistent between the train and the test accuracy. It's really jittery still, but the trend is following more closely. So next we're going to increase or decrease the learning rate, which requires us to further increase the epochs. So far I've been keeping the epochs lower so that I can keep the test time down. This takes about 2 minutes to test 10 epochs. It's going to take about 10 minutes to test 50. So let's keep going. But when I decrease the learning rate, I need to increase the epochs, or else because the learning rate, when it decreases, you need more epochs to get this, the same amount of training. However, the training is more, what's it called? It's more consistent. You don't have as much jitteriness with a lower learning rate. And we're going to see that right here. The train accuracy and the test accuracy, along with the loss functions, they follow the same trends, and the test accuracy is less jittery, and the train accuracy is consistently improving to about 30%, which is the best so far. Model 4 is the best performing model we have so far. It's also the most consistent between the train and test accuracy. Next, we're going to change our model architecture a little bit, and I'm going to use the same other hyperparameters as we did for this model, Model 4, but for Model 5, we're going to create a new model that incorporates one single ReLU function between these two linear functions. And the ReLU, the way it works is basically if you have a, here, let me show you a picture of ReLU graph. So if your value is less than 0, it's going to be equal to 0, and if it's greater than 0, you're going to take the x value as your y value. So it's linear if it's greater than 0, and horizontal if it's less than 0. It creates some nonlinearity and helps it train better. But as you can see, these are the exact same as above, these hyperparameters. And what do we get? It trains better. Before we saw about, 30%, and now we get up to 35 and 34% roughly for the training accuracy and testing accuracy. You can see the losses are also still consistently decreasing for both. Model 5 is the best performing model so far, so we're gonna, it's important that all the other hyperparameters were the same except the model that was run on, because that means that we're going to use this nonlinear function with the RelU for the rest of the project, for the rest of the models. We're also going to experiment with changing the optimizer from stochastic gradient descent to this Adam W algorithm, and what does that do? Well, I don't really like what it does. Even though the training accuracy is higher on the same number of epochs, it's at about 38 or 39, and the test accuracy seems to plateau at about 36. And this is bad because it's overfitting to the training data and not fitting to the accuracy data. So at this point, I'm going to reject Model 6 and continue to accept Model 5 as the best one so far. There were minimal improvements in the maximum, testing data set, and it's overfitting to the training data set. Model 7, we're going to increase the number of hidden units, still with our same epochs and learning rate. We're using SGD, as you can see here, and nonlinear function model. So when we go through that, it improves from our Model 5 to Model 7 from 35 to 36. So that concludes that increasing hidden units even more, it does improve your model, but you get diminishing returns because we went from, I believe, 64 to 512, which is 8 times higher, but we only got an extra 1% accuracy. So at this point, I think I've gotten the model as good as I can get it, except for I can train it for longer. And this one takes about 15 minutes to train. So if I'm going to train it for longer, I want to make sure I have it as good as you can. So here's my Model 8. It's my final model. We're going to use 250 epochs in increments of 50. I tried to, save it to a dictionary within a dictionary, but it didn't quite work, and I didn't want to wait an extra 75 minutes. However, that's okay, because it's still trained for the full 250 epochs using 2 for loops. And I was still able to graph my loss curves and accuracy curves. And as you can see here, it starts to become overfitted, but it is not quite overfitted yet. Actually, I looked into it, and at this point in the graph right here, it will start to go up like this wards after here. And at the minima between the test loss along all the epochs is where your most optimal, best fitting model is. So here's our loss function value, and here's our test error. And at the minima, that's where it's the best fit of the model. So the number of epochs is best fit. Honestly, I'd say it's pretty close to 250. Maybe if you went up to 275, that would be best fit, but the increases would be marginal. And we get an overall test accuracy score of about, I think that is 44%. Yeah, here I say it. And that is the image I just showed you. And we trained it for 250. It's pretty close to the optimal training time, as we saw in that image. And it is much better than the original score of 25% on 2 epochs. and it is significantly better than randomly guessing at 10%. Looking into our results now, I'm going to visualize the model using a confusion matrix. I'm running quite over on time, so I don't really want to explain this, but I could. But very basically, we are going to get the total values. We're going to get the prediction tensor, and we're going to compare it to the true value tensor for the testing model. And we're going to go through the entire, all 313 batches for that to get the predictions. And of course, we're using inference mode and eval and model 8. And then we're going to create our confusion matrix. I use sklearn and their confusion matrix. And that's what seems to be easiest for me, and it worked. Here's my confusion matrix. It's very, very pretty, very bright colors. You have the color scale here. Here's the true values, and here's the predicted values. So if we predicted airplane, we got airplane 35.9% of the time. And then it's very cool the things you can look into with this. Here's some interpretations I wrote down. Ships have the highest accuracy score of 56.7%, and the most mistaken prediction is done between truck and automobile, which is interesting given that there is no pickup truck. And it's also interesting given that the automobile and the truck have very high prediction scores. They were able to not predict for everything else, but then have a good 20% plus 15%, 35% of the time it was wrong, just because it chose the other one. And funnily enough, cats and dogs was the next highest. Cats here, dogs here. This 13.4 and the 18.8. About 30% of the time it was wrong because it guessed wrong between cats and dogs. But cats was our worst performing image. So in conclusion, model 8 is the best one using the nonlinear model I created above, and combination of linear and ReLU functions with the following hyperparameters and 250 epochs. Some ways I would further improve the model would be through changes in model architecture, such as adding more hidden layers. So I changed the number of hidden units, but I never added an extra hidden layer. You had the input layer, the first hidden layer, and the output layer. Possibly by adding an extra hidden layer, you could improve the model, or changing the type of model to a convolutional neural network. I attempted this, but did not have much luck. And changing the model to an architecture to accept RGB values instead of grayscaled images could improve performance because you have more data. It's possible that you wouldn't get things like birds and deer mixed up because birds are different colored than deer. However, that's okay. Here are my references, and I am going to be finished. I had a great semester, and this was a lot of fun to learn about. I mostly learned through applying the things we learned in class to a video here that used a different data set, and I borrowed code and I edited the code to work on my data set for CFAR 10. Then I also went through PyTorch documentation and read about the CFAR 10 dataset. Thank you very much.